Hello everyone, welcome back to this channel. In this video we are going to look at today's LeetCode daily challenge, and the name of the problem is graph bipartite. So we'll be given an undirected graph with n nodes where each node is numbered between 0 and n minus 1. We'll be given a 2D array graph where graph of u is an array of nodes that node u is adjacent to. Okay, each index represents a vertex, and corresponding to that vertex we will be given a subarray which comprises of all the vertices this current node u is adjacent to. We are also given some properties. Firstly, there will be no self edges. Okay, also there are no parallel edges in our graph, and since our graph is undirected, so if vertex v is in graph u, then vertex u will be in graph v. Okay, also it is given that graph may not be connected. There can be multiple components such that there is no path between two nodes. We need to determine whether a graph is bipartite or not. A graph is bipartite if the nodes of the graph can be partitioned in two independent sets, set A and set B, such that every edge in our graph connects a node in set A and a node in set B. So this is the definition of bipartite. Now let us understand the approach of this problem. So we need to check whether the given graph is bipartite or not. It is also referred to as graph coloring. Okay. In other words, we can define a bipartite graph as a graph that can be colored using two colors, such that no two adjacent nodes in our graph have the same color. So we saw this definition given in the problem statement. So this definition can be reframed as this informal definition of bipartite graph. Now we'll see some examples to get some clarity on this problem. So let us consider our first example. Let's say this is the graph that we are having, and the nodes are numbered from 0 till n minus 1. So to start off, we need two colors. Let's say we take color red and we will represent it by integer 0, and the other color that we will take is color blue, represented by integer 1. Okay, currently we are not writing any algorithm, we will just try to get some clarity on this problem. So we will begin with node 0 and we will color it red. Okay, then we will move to its adjacent node, which is node 1. Two adjacent nodes should be colored with different colors, right? So we need to color this node as blue. Like this we are going to progress. Next, now the adjacent of node 1 is node 0 and node 2. Since node 0 is already colored, we don't have to revisit this node. We will move to node 2, right? Now node 2 should be colored differently than node 1. So node 2 we are going to color it red. The neighbors of node 2 are node 3 and node 5. So we are going to color node 3 as blue, since the previous node is colored as red. Depending on which algorithm we use, if we use DFS algorithm, then we will keep on moving ahead. We will move to node 4 and then node 7, like this. And if we use BFS algorithm, breadth first search algorithm, then after coloring node 3 we will color node 5, right? Because in BFS we move level wise. Okay, so let's say currently we are talking about breadth first search. So after coloring node 3 we will color node 5 also. Node 5 will also be colored as blue, since the previous node of node 5 is node 2 and we colored it red. Then again we will move further. Now we come to node 4. We are going to color it as red, since the previous node was colored blue, right? The same way we are going to color it red again, since node 5, which is adjacent to node 6, was colored blue. After coloring node 4 and node 6, we have node 7. Now both node 4 and node 6 were colored as red, so node 7 we are going to color blue. Again we will move ahead to node 8, which is the neighbor of node 7. So node 8 should be colored as red, since we colored node 7 as blue. Okay, and then coming to the last node, which is node 9, we are going to color it as node blue, because the previous node was colored as red. So after coloring all the nodes of this graph, we can see that no two adjacent nodes have the same color, which tells us that this graph is a bipartite graph. Okay, we can consider that color red is set A and color blue is set B. So in this graph, as you can see, every edge connects a node from set A to a node from set B. Hence it is bipartite. I hope it makes sense. Now let us consider another example. So again we will begin with node 0 and we will color it red in the beginning. Then coming to node 1, we must color this node with a different color, right? Then the adjacents of node 1 are node 0, 2 and node 3. As we have already colored node 0, we are not going to revisit it. We will move to node 2, and node 2 should be colored with a different color. It should not be colored blue. Okay, the same way node 3 should also be colored as red. Now the adjacent node of node 2 is node 1 and node 5. Node 1 is already colored, so we will move to node 5 and we are going to color it blue because its previous node was colored as red. Then coming to node 3, the adjacent node of node 3 is node 4 and we are going to color node 4 as blue, since the previous node, which is node 3, is colored as red. Here I would like to stop, and as you can notice that node 4 and node 5 are adjacent nodes, but both of them are colored blue, which is wrong, because according to the bipartite definition, two adjacent nodes should belong to two different sets, two different colors. It means that this graph is not bipartite. So here I would like to make a remark that if any graph does not contain any sort of cycle, so any such graph is a bipartite graph. As you can see, all the adjacent nodes are colored differently, so any graph which does not contain a cycle is surely a bipartite graph. But when a graph contains a cycle, we need to determine whether that graph is going to be a bipartite or not. Observing these two examples, the first example, number of nodes which comprises of cycle are 1, 2, 3, 4, 5, 6. there are 6 nodes in a cycle and this graph was bipartite. Coming to the second example, we are having 5 nodes and this graph is not bipartite, right? So any graph which does not contain a cycle is surely a bipartite graph, and if a graph contains a cycle, then if the cycle is formed with even number of nodes, then that graph is going to be bipartite. But if there are odd number of nodes in a cycle, it will not be a bipartite graph. So this was the remark. Now talking about how we are going to solve this problem. So all we need to do is traverse through the graph. As we all know, there are two traversing algorithms, BFS and DFS. So we can use both of these algorithms to solve this problem. All we need to do is we need to keep track of the color of the nodes that we have visited. So I will show you the code of two approaches one by one. Firstly, we are going to see the code to solve this problem using DFS. So this is the C++ code of depth first search. Firstly, we are finding the size of our graph, which is the number of nodes present in our graph. Then I have initialized a color array for n nodes in our graph, and I am initializing the color of each node as -1, which means that that particular node is unvisited currently. Then we will iterate through all the nodes in our graph. It was mentioned that our graph may not be connected. There can be multiple components. Hence we will traverse through all the vertices one by one. And if the color of a particular vertex is -1, it means that that vertex is unvisited. It means that that vertex is the beginning of a separate component in our graph. Hence we are going to check that component. So here we are calling our DFS function. We are passing current node value. We are passing our graph 2D array. Then we are passing our color array also. And if this function call returns false, it means that this particular component cannot be colored the way we want to color it. Hence we are going to return false, that the graph is not bipartite. If all the components are colored appropriately, we will return true, stating that the current graph is bipartite. Okay, now let us see this DFS function. In this function we will be getting the current node. So if the color of the current node is -1, we are going to color it first. So here I am initializing the color as 0. It can be any color. Now we are iterating through the neighbors of the current node using our graph given to us. If the color of the neighbor is -1, it means that we need to color that node. So we are initializing the color of neighbor as 1 minus the color of the current node. Okay, so if the color of the current node is 0, so 1 minus 0 will become 1. And if the color of the current node is 1, so 1 minus 1 will become 0, so color of the neighbor will become 0. And after coloring this neighbor node, we are making a function called by passing the neighbor node along with graph and our color array. And if that function call returns false, we are going to return false. Else if the color of the neighbor node is equals to the color of the current node, which means that that neighbor node is already visited and the color of that node is equals to the current node, which we are having, then also we have to return false, right? Otherwise at last we are returning true. So this is a simple DFS. All we are doing is passing an extra color array to keep track of colors of each node. Okay, and on submitting, this code will get accepted. So as you can see, it got accepted. Time complexity of this code will be same as the time complexity of traditional DFS algorithm, which is big O of n plus e, where n is the number of nodes and e is the number of edges in our graph. Now let us see code for BFS approach. Now coming to the BFS algorithm, this part of the code will remain the same, only the function name we have changed, and this is our BFS function. So here I have initialized a queue data structure, first in first out, and I am pushing the current node in our queue, and also this beginning node we are initializing its color with 0. Okay, then while our queue is not empty, we will perform our BFS. So each time we will first determine the number of nodes present in our queue, then that many times we are popping from the front of our queue data structure, and we are going to check the neighbors of this current node using the graph 2D array. If the color of the current node is equals to the color of the neighbor of that node, then we are returning false. Else if the color of the neighbor node is -1, it means that that node is not colored yet. So we are initializing, we are assigning the color of the neighbor node with 1 minus the color of the current node, like we discussed before, and we are pushing the neighbor node in our queue for the next levels, right? So this is also a very standard BFS algorithm, and at the end we can return true. Time complexity of this algorithm is also big O of n plus e, which is the time complexity for BFS, and on submitting, this code will also get accepted. So to conclude, you can go through this summary of the two approaches that we discussed. So it was a pretty simple and interesting concept. If you are new to this channel, please consider subscribing and also share it with your friends and juniors. Thank you.